Hello everyone and welcome. My name is Jason Gregerson. In this video we're going to continue our discussion about applications of integration. Specifically we're going to look at arc length and surface area. We'll start by looking at arc length. Our goal is to find the length of the curve y equals cosine of x plus x on the interval from 0 to 3. So we're going to follow the same general approach we did in the previous video. I don't know how to calculate some value. I don't have a formula for the length of a curve. However, if I view the curve on a small enough interval, in other words, I look at a little slice of the curve, well then I could approximate the curve with a straight line. I'll call that segment ds, a little slice of the arc length. Now I can also think of that line segment as the hypotenuse of a right triangle, whose legs are the change in x and the change in y on that interval. And once I have that relationship, I can then write an expression for the little segment of arc length. Using the Pythagorean theorem, I can write that as the square root of dx squared plus dy squared. Now, if I take that expression and I do a little algebra with it, I could factor a dx squared out from under the radical, and the result would be the square root of 1 plus dy dx squared dx. However, I could also do some different algebra where I factor a dy squared out from underneath the radical. In that case, my expression for ds would be the square root of 1 plus dx dy squared dy. Both of these would be valid expressions for a little segment of the arc length. They'd be good approximations. And now back to our general approach. To find the total length of the curve on this interval, I have to add up all my slices continuously. So now I have two different formulas to calculate the arc length. Which one am I going to use? Well, my curve is given to me as y is a function of x. Y is equal to cosine of x plus x. That means it's easy for me to calculate dy dx. So I will use this first equation. Now let's do that in Mathematica. So I need to integrate the square root. I'm going to hit Control 2 to get the nice square root notation. 1 plus my derivative, so f prime of x squared. And I'm going to integrate that from 0 to 3. Now when I hit Shift-Enter to evaluate that, you'll notice that Mathematica pauses. In fact, if I go over to the right-hand side here, I can see the cell is colored black. That means Mathematica is working trying to evaluate this. However, what we'll see is that these integrals tend to be very challenging to generate. So in fact, what I'm going to do instead is I'm going to go to Evaluation. I'm going to abort my evaluation because it's taking too long, and I'll realize that this is an excellent case for me to use n-integrate and do a numerical technique. So now I've modified it from integrate to n-integrate. Now when I hit Shift-Enter, it gives me a value right away. I should always think, is this value, does it make sense? Is it a reasonable value? And so if I look back at my curve, I said if I traveled from x equals 0 over x equals 3 just in a straight line, well, that line would have a length 3. And so for me to go vertically a little bit, I would expect a value that's slightly bigger than 3. So my value of 3.26552 certainly seems reasonable. Our next question is, how far down the road can I travel? The idea here is that we integrated from 0 to 3 to find the length of the curve as we traveled over that interval. But the question is, if I could only travel a total length of 2, where would I end up along my curve? So we could certainly modify our integrate command to explore different points. I could integrate, for instance, from 0 to 2, the square root of my expression here. And I could find that specific value, or 2.5 or 2.3, and I could explore that. Or what I could do is I could integrate from 0 to some parameter value like t, and the result then would be a function of t. And so I could think of the arc length here as a function of t. Now in my specific case, I have a target value. I'm trying to figure out where I'm at when I've traveled a total length of 2. So I would just have to evaluate this right-hand side and then take the expression and solve that thing for t. And that's what I'll do in Mathematica. So here I can just multiply my command to integrate not from 0 to 3, but from 0 to t. and then I want to set that equal to 2 and solve the expression for t. Of course, I had to use n integrate instead of integrate because this expression was already complex. So in this case, I will also use find root instead of solve to find my value here. So for find root, I have to put in my variable and also a starting point for the algorithm. Via the picture, I can have a guess that a reasonable starting point would be 2. And so if I evaluate that, it will give me some error message based on the fact that I have a parameter to my integrate, but the value I get also matches my expectation. So I can be confident that t equals 1.8413 is the x coordinate of the point that I would reach. To find the y coordinate, I would just plug this value into my original function. So now I've been able to answer that question. Next, we'll look at surface area. Surface area. So the problem here is to take my curve and rotate it about the x-axis. In doing so, I generate a surface, and the question is, what's the area of that surface? So first, let's think about the process. Here's my curve, and if I rotate that curve about the axis, let's spin this so we can see this a little more clearly. I'll continue to rotate about the x-axis. We can see that this is the surface that I would be generating. Now, following our general approach, however, I don't know a formula for the area of this curved surface. So instead, what I'll do is I'll look at a little slice of the surface. Here's my little slice. And so if I can find a representation for the area of this slice, then I can add up my slices to find the total surface area. Now, the slice might not look like it. It might look a little more elliptical, but that's just the aspect ratio. The reality is this slice is a little circle with a little bit of a thickness here. So our construction is to take a little piece of the arc length, our little ds, and rotate it about this circle. The distance it would travel around that circle will be the circumference of that circle, which we can write as 2 pi r. So if I take the arc length times circumference, it should give me an expression for the surface area of my slice. So my surface area, a little slice of that surface area, can be represented as the circumference times the width of my slice. That means to find the total surface area, I would just add up all my slices continuously. Now, depending on which axis I'm rotating about, will tell me my value for r, the radius value. In this case, because I'm rotating about the x-axis, because I'm looking at a surface area rotated about the x-axis, well, then the radius value is the distance from the x-axis up to my function. And if I looked at that point, that height would be the y-coordinate of that point. So in that case, my radius value would be equal to y. So I can rewrite, if I choose, my surface area formula to be 2 pi y ds. Now, I already have two expressions for my ds. I have one represented as a function of x and one represented as a function of y. And so depending on which ds I choose will depend whether I can leave my radius value as y or I need to rewrite it as a function of x. And of course I can do that because I have an expression for y as a function of x. So in my specific case, I know that I can use ds 1 plus the derivative squared just like I did in the previous problem, and that would result in my ds being a function of x. So in that case, I would just have to replace my y value with what it's equal to with respect to x. And in this case, that's cosine of x plus x. And I would then integrate that from 0 to 3. So now let's actually do those calculations in Mathematica. So I want to look at the square root of 1 plus f prime of x squared. I'm just going to run that so we can see what that expression looks like. It really is a function of x, which means that when I put in my 2 pi times my radius, I need my radius also to be a function of x. In this case, that expression is cosine of x plus x. And so this is the expression that I want to integrate over my interval. So then before this, I will type in the n integrate command, because these tend to be complicated integrals. And I'll integrate this from x goes from 0 to 3. And when I evaluate that, I'll get my value for the surface area. Now what if we rotated about a different axis? In this problem, I like to rotate about the y-axis. So once again, let's visualize the system first. So if I rotate this about the y-axis, here's my rotation, and I can explore the surface a little more down here, I generate a different surface. What's the area of this surface? Well, let's follow that same process. Let's look at a slice. Now once again, in the same case, we're going to take that arc length and rotate it around some circular path. So my expression for the surface area rotating about the y-axis starts in the same place as it did when I was rotating about the x-axis. In other words, my surface area is going to be the integral of 2 pi r ds. Just like before. The difference is the radius value. Now my radius of that circle of rotation is going to be the distance from the y-axis over to my function. That coordinate of that point of the function, the x-coordinate would represent this horizontal distance. So that radius value I can write as x. So if I want, I could rewrite this as 2 pi x ds anytime I'm rotating with the y-axis. Now the question is, if I, depending on the ds representation I choose, I might leave my radius as x, or I may have to convert it into a function of y. So in our last problem, we use ds to be the square root of 1 plus my derivative squared, and this resulted in a function of x. Because that's a function of x, I can leave x in for my radius value and just integrate that over my interval. Now let's do that calculation in Mathematica. So now once again, I'm going to look at the square root of 1 plus f prime of x, quantity squared. And once again, we'll run that. We can see it is a function of x. So now I have 2 pi times x out front. And now I can really just leave this value x in here for my radius. And this is the thing that I want to integrate. Once again, I'm going to use n-integrate. And integrate this over the interval x goes from 0 to 3. And now I have this value for this new surface area. Lastly, you might be wondering, what happens if I don't have y as a function of x, but rather I have x as a function of y? So here's a different curve, and this curve fails the vertical line test. So that means I can't represent it as y as a function of x. So in this case, I'd want to use a different representation for my ds. So in this case, I'd want to represent my ds as the square root of 1 plus dx dy squared dy. Now I have my arc length represented as a function of y, which means if I did my surface area calculations, I have to take that into consideration as well. So now we can calculate all our values once again using this curve. So here is my new representation for this. Here x is a function of y, so I'm going to store that into some function name. I'm calling it g of y in this case. And so now if I want to find the arc length, I would take the square root of 1 plus g prime of y squared, and I would n-integrate this expression as y goes from 1 to 2. And I would have that value. Now what if I wanted to take this curve and rotate it about the x-axis? Well, in that case, I'd have to multiply by 2 pi and my radius value. In this case, the radius value would be y. If I'm rotating with the x-axis, that's the height from the axis up to my curve. And now the question is, do I need to use just y, or do I need to convert it to a function of x? But because my integrand is now a function of y, I can just leave this radius value of y. So this would be the surface area I would attain by rotating this curve about the x-axis. What if I rotated about the y-axis? In that case, my radius would be the horizontal distance, the distance from the y-axis over to my curve. However, my ds expression is a function of y, so that means I need my x to be a function of y. So that means I'd have to replace my x expression with y cubed minus y squared, the representation of x in terms of y. I'd evaluate this, and this would be that surface area if I rotated about the y-axis. All right, so we've done all the different examples of arc length and surface area. That concludes this video. Thanks for your time.